Okay, thank you very much, Claire, and thank you all for coming. I'm just going to start with some thank yous, and these are basically all the people who have contributed in a big way to the stuff I'm going to present today. There's some from the past. Up here is my PhD supervisor, Graham, looking very serious with a diamond. This is Simon, who was a former PhD student I worked with in Copenhagen, and he did some of the work that I'll present. Sarah is Graham's lab manager at the University of Alberta. And Chris was my postdoc supervisor in Copenhagen. And then over here we have Rasmus, who's actually a Dane, but has ended up in Canada for 15 years or so, who I've been working on this ERC project that I'll present a bit. Emil, who's doing a PhD with me now, and Kara, who's also a PhD student, and then Shreya and Dakuya, who are postdocs in my lab. So yeah, just a thank you to all of them, because obviously no scientific endeavor is done alone. For the talk today, I'll give a little bit of an introduction to chromite, and I'm going to try and crowdsource it a bit, because that way you don't only have to listen to me speaking. So I'll go through what is a chromite, talk a little bit but not much about chromatites, and then talk about how chromite compositions behave in lavas. I'm then going to move on to some work I did on the Ujaragsra intrusion that was previously thought to be among the oldest rocks on Earth. And I'll talk about how we can use chromite compositions to get at parental melts and tectonic settings of rocks of unknown origin. And then hopefully all this will build into how we can use detrital chromite to trace mafic crustal growth on Earth. And I'll talk a bit about the problem of crustal growth in general and why this has been traditionally a felsic problem, and then move on to what chromite can tell us. So, introduction to chromite. I would like all of you to turn to the person next to you for a minute and tell them something that you know about chromite. If you know nothing about chromite, I want you to spend that minute engaging in wild speculation. Okay? So, off you go. Okay, so I think for a lot of you that's as much as you've ever thought about chromite. So first I want to hear, did anyone have any wild speculations that they would like to share? Yes, some, or you're all very knowledgeable about chromite. It's not magnetic.
It might be, I don't think it is. No, it's not.
Okay, cool. Anything else? That's a good one.
It's ultramafic.
It's ultramafic. That sounds like confident knowledge. I think that was yeah. So nothing super wild then.
It's artisanally mined if it's further.
Okay. That actually sounds quite convincing to me. Does anyone have something more concrete that they wanted to share that they're a bit more confident about?
Contains chromium.
Excellent. Okay.
Loads of it in Bushveld.
Loads of it in Bushveld. Yeah. Okay. We're starting to hone in on the truth here. Anybody else?
Yeah. It's opaque under light microscope.
Okay. So most of those were in the right kind of direction. So let's talk about what I know about chromite. Okay. So chromite is an early crystallizing mafic, ultramafic mineral. It's a spinel. With my pointing stick, I can show you that means it has this general formula of A2+, so 1 2+ cation, 2 3+ cations, and a bunch of oxygens. I use chromite in the very loose sense because I'm not a chromite expert. So for me, any spinel that has a significant amount of chromium, I'll call it a chromite. Some people can fight me on that. It's generally these small equant grains, and you will find it often included in olivine or sometimes in the ground mass of lavas. About 20 microns, up to the intrusive ones can be on the large side, about 1,000 microns. It's a cubic mineral, which means it's opaque and cross polars, and it does often look opaque, like these kind of look black, but it's not actually. If you have a thin section that's cut too thin, then you'll see it's got this beautiful red-brown color, sometimes a little bit on the yellowish-brown side, but it's only opaque in the case where it has a very, very high magnetite content. Speaking of which, magnetite is also a spinel, so chromite is a little bit magnetic. Just a bit like that. Okay. Chromite is also a major host of chromium and some platinum group elements. So if we're looking at bulk rock data, and I've shown here, this is just a bunch of komatiite lava samples and plotting the chromium against the magnesium contents. And when chromite has saturated, you can see it drops pretty smoothly. And basically, if we back project this, you can see that it falls on a mixing line between olivine, which has a little bit, but not very much chromium, and chromite, which has, typically about 30, 40, 50 weight percent chromium. And so it's crystallizing in very, very small amounts. So 1% chromite is enough to explain this trend. So as soon as chromite starts to crystallize, then bulk rock chromium content starts to fall. Another indication we might see in bulk rock data that chromite is present is when we see correlations between ruthenium, which is a platinum group element that is concentrated in chromite, and chromium. Okay. Chromite compositions partly reflect source compositions, and there's a very, very big asterisk on this. But I've just shown here in a very simple chromite ternary plot between chromium, Fe3+, and aluminium, which are the main constituents on that 3+ cation site. You can see that chromites from different tectonic settings, different magma types, different placement styles will often plot on different fields. But I plotted up a bunch of data, all from chromite from the same intrusion here, and you can see that it does vary a bit, and also there's a lot of overlap between these different major element fields. Chromite is also really robust, just kind of during everything, especially compared to other mafic minerals. So it's pretty robust during metamorphism. It will survive to very high metamorphic grades. It survives weathering, erosion, and transport. And the result of that is we can see sometimes in these meta-sandstone rocks, we'll get heavy mineral layers that are just full of chromite, and it kind of survives the whole process. There's another example down here. Finally, we can date it, another asterisk here, using the rhenium-osmium system. And this is strictly a model age, it's not a real date. But the way this works is we have some idea of the mantle evolution of rhenium and osmium, where 187 osmium is formed by rhenium 187 decay, and over time the mantle evolves from some kind of primitive solar system osmium isotope ratio, and it grows upwards. Most mafic and ultramafic melts that come from kind of typical mantle sources, you can just project these back onto this line because chromite excludes rhenium and takes in a lot of osmium. And then from that you can essentially read off the age. And this is a probability distribution of some real chromite osmium data, and you can see we get a pretty nice age around 3.1 billion years old. The big problem here is that the main uncertainty in this comes in our uncertainty about the mantle composition, so it doesn't matter how well we can date the chromites, our ages are never going to be better than plus or minus 100 million years. Okay, I will very, very quickly talk about chromatites. So chromatites are broadly divided into stratiform layers. You can see some really nice chromatite layers in a metamorphosed dunite. And then we also have pods. And these are called podiform chromatites. And in general, people divide these into podiform and mantle chromatites and stratiform from layered intrusions. But this distinction doesn't really hold. Both of these are actually from the same intrusion and quite a small intrusion, and you can see there's completely different appearances. So generally, stratiform intrusions, podiform comes from the mantle, but it's not a strict rule. There's also a lot of problems and a lot of research into chromatite formation. Just to cover that really, really briefly, like we said before, that a cotectic olivine chromite crystallization proportion is 99% olivine, 1% chromite. But we'll see in a lot of intrusions, we see chromatites that are basically approaching pure chromite compositions. So if you have a 50 centimeter thick chromite layer, this is equivalent to about 50 meters of magma thickness. And in this particular intrusion that I'm showing some pictures from, there was a lot of chromatite compared to the size of it. But I'm just going to neatly sidestep these and completely ignore them in this talk because I'm not that fussed about how chromatites formed, much more interested in what we can do with it. So how I got started, and as I said before, I don't really consider myself a chromite expert, but I was researching komatiites and I was trying to figure out a way of recovering the oxygen fugacity which I needed for calculating eruption temperatures. And what you can see here is that this is a plot of the Fe2+ as a proportion of total iron of a melt in equilibrium with igneous chromites. And along the x-axis here is the olivine chromite equilibrium temperature, which is based on iron and magnesium exchange. And we actually see like a massive, massive spread in the iron 2 plus over total iron ratio. But you can see that it correlates really, really strongly with this equilibration temperature. And if we back project this to the range of magmatic temperatures that we measured independently, then we get an iron 2 plus over total iron of about 0.9. And this is what has been measured using much, much fancier methods in other komatiites. And we recovered an oxygen fugacity of about QFM plus 0.75 that was again independently corroborated. So I think this shows that we can get useful information out of chromite even when we're not fussed about how the chromite formed, we're just trying to study the magmas that it comes from. But the big downside here is this whole trend is driven by, as olivine and chromite equilibrate just from the magma cooling, these are very, very low-grade metamorphic rocks. The chromite is basically sucking iron out of the olivine and trading it for magnesium. So subsolid disequilibration affects basically all chromites, and especially the 2+ cations. You can see here, this is comparing a model of fractional crystallization of chromite from the same melts, and all of the actual measured chromite compositions fall to the high iron, low magnesium side of this. And if we look at intrusions from the same belt, which we think have the same parental melt, then the trivalent cations can also be affected, and this is probably from late exchange between an interstitial melt in a cumulate and the chromite itself. So subsolid disequilibration is a big problem, and we should never ever trust 2+ cations in chromite. Okay, so just to wrap that section up, chromite is an early crystallizing mafic ultramafic mineral. It's pretty robust. It can carry a lot of useful information about the magmas or rocks it crystallizes in, but we have to be careful with it. Chromatites exist, and I won't say anything else. And chromite can be dated using rhenium-osmium modulators. Okay, the next section is about the Udra-Exmouth intrusion, and I usually preface this with saying it was 1 week of fun, 3 months of pain. So I had a really great time in Greenland doing fieldwork and sampling and mapping this intrusion, and then I was literally chained to a mass spectrometer running 12-hour-long analyses. I would set one running in the morning, deal with that all day, then I'd set another one running in the evening, go to sleep, wake up just in time to collect the data and do the post-run stuff that we had to do. So this was not a fun time in my life, but we got some cool data out of it. So what is the Udra-Exmouth intrusion? It's a layered ultramafic intrusion. It's in the North Atlantic craton, which is shown in pink here, of Greenland, and it's actually about 20 kilometers or so south of Ishua, in the kind of higher grade gneisses. We see little enclaves of ultramafic rocks and mafic rocks, but there's no coherent supercrustal sequence here. It's mainly made of dunite, harzburgite, and chromatite, and we have some really nicely preserved igneous features. It's not super clear on the screen, but you can actually see there's almost like onlapping patterns of chromatite layers that seem to have grown in a little channel at the base of the magma chamber. And it's hosted in 3.8 billion year old gneiss. So why do we care about this little intrusion in Greenland? Well, because it is of the way it's hosted as an enclave in the gneisses, it's been interpreted to be older than 3.8 billion years old, which is the age of the gneisses immediately by the intrusion. There's also this paper from 2013, which suggested that it might be as old as 4.1 billion years old from platinum osmium. Basically, they dated a bunch of different samples, and one sample came out with a 4 to 4.1 billion year old age. This would make them among the oldest rocks on Earth, certainly the oldest chromatite on Earth. This intrusion also has some accretionary ruthenium isotope anomalies, and it basically tells us that the source of this intrusion was depleted in carbonaceous chondrite components compared to the modern bulk Earth. And so it seems to have come from a source that hadn't fully received a full complement of late accretion. So lots of interesting stuff going on. But you might ask, why would we use this platinum osmium system? It's quite an unusual one for getting ages. And really, these kind of high-grade ultramafic rocks are very, very difficult to work with. There is obviously no igneous zircon that won't saturate for a long time. They have very, very low concentrations of neodymium, hafnium, lead, and strontium. That means that they're very, very easily crustally contaminated. And then they've been through amphibolite fascies metamorphism, which means that a lot of different isotopic systems can be disturbed. And this is another earlier study by Cognital, 2015. And you can see this is the minimum age inferred from the gneisses, and they have a huge scatter of rhenium-osmium ages, mainly going towards younger ages than the inferred age. So because platinum is less mobile during metamorphism than rhenium, there was this idea that maybe platinum osmium ages are preserving this 4.1 billion year old age, even with the rhenium osmium is totally messed up. But the platinum osmium system, to me, is probably the worst geochronometer in use. Maybe others have worse ones, but it's pretty terrible. The reason for this, 190 platinum, which is the parent isotope, only constitutes about 0.01% of the total platinum on Earth. Those of you that know PGEs can probably guess that platinum is not super abundant. It's generally present in very, very low concentrations. And on top of that, when it decays by alpha decay to 186 osmium, it's got a half-life of 469 billion years. So this means for typical mantle composition and solar system starting 186 over 188 osmium ratio, over the entire of Earth history, 4.5 billion years, we expect about 100 ppm of variation in the 186, 188 osmium ratio. This means that for every 12 parts per million uncertainty in our measured osmium isotope ratios, we expect an age uncertainty of 500 million years, which is not great. On top of that, there's this bonus 500 million year age uncertainty from the uncertainty in the solar system initial. Typically, when people measure this, they get precisions of about plus or minus 30 parts per million. So each analysis gives you an age plus or minus 1.5 billion years. It's not great. This is just kind of showing this schematically, whereas if we don't propagate the errors properly, we just take the worst case scenario on our precision, we measure a ratio, we project it back to the mantle, we can get ages between basically the start of Earth history and a billion years. So how do we approach something like this? Well, to start with, zircon ages are a lot better than platinum osmium ages, so we started by doing some really, really detailed mapping and uranium, lead, and zircon. And basically we were trying to confirm this 3.8 billion year minimum age. And then we focused in on massive chromatites, which have really, really high osmium concentrations. Okay, it's 200 parts per billion, but for osmium this is a lot. And then basically a brute force analysis approach to analyzing 186 osmium. So this is why I spent 3 months changing my spectrometer, analyzing it over and over and over again. So for the 3.8 billion year old minimum age, and this is absolutely incredible map made by Simon, the former PhD student, and this was based on field mapping that we did, and then we took some high resolution drone photos to get everything kind of in the exact position and in proportion. You can see it's a pretty small intrusion. It's about 50 meter scale, so this is about 400 meters long, I think. And what we see is the ultramafic rocks, mapped here as dunite in blue, are never actually cross-cut by the 3.8 billion year old gneisses. So they're always wrapped. There's this kind of like sheath of younger granitoids around them, splitting off the ultramafics and the gneisses. And these are all 2.97 billion years old. So actually the only minimum age constraint we have is that this is older than 2.97. And then with our many platinum osmium dates and combining them with the earlier ages, we found that all of these ages are actually identical within uncertainty. Remember, every single one is plus or minus 1.5 billion years. So when we average all of our data and all of the previous data, we come up with this average age, 32 analyses from 7 samples, which gives 3.44 plus or minus 0.29 billion years old. So this is relatively young, and it certainly doesn't seem to need a 3.8 billion year old age, let alone 4 billion. But there is this systematic uncertainty that we talked about before, and that gives us an extra plus or minus 500 million. So is it possible that even though our average is down at like 3.4, that the real age is kind of 4.1? Well, when we look at the rhenium osmium ages, all of the kind of like freshest, least altered chromatites give this very, very precise age of 3.23 plus or minus 4 million years. So this is 32 analyses from 7 samples. So this is how precisely we can actually measure 187, 188 osmium. But we've also got that 100 million year systematic uncertainty. So plus or minus 4, got to take it with a grain of salt. So I think it's really, really unlikely that these are actually 4 billion years old, because we basically got a concordant 187, 186 osmium age, similar to what people do with lead isotopes and zircons. And it seems like it evolved from a typical chondritic source. We're kind of along the average chondritic evolution that we'd expect. And we also did osmium stable isotopes that I don't have time to show here, but that also agrees with a chondritic source. On top of that, it's consistent with some hafnium model ages from these rocks, which also come out around 3.2. And I think the big point I want to make here is that chromite, rhenium, osmium can record meaningful ages. This is consistent with the minimum age constraints, it's consistent with the hafnium isotopes, and we've got agreement between our 186 and 187 osmium. Okay, so Udrexford is really young, but where did it come from? And I put Akiya's photo up here because this is actually mostly his work. But previous work on this intrusion had come up with a range of possible ultramafic parental magmas that you could produce something full of dunite from. And so the options are basically, could have come from a komatiite. This is an ultra-hot Archean lava, and it would imply some kind of plume source. It could have come from a bonanite. This implies that it has a very depleted source and of some kind of flux melting in a subduction zone. And finally, it could have been something else, maybe a pickrite or a high magnesium basalt. But how do we go about figuring out the origins of something that's been through so much high-grade metamorphism? So the Udrexford rocks have been through at least 2 phases of amphibolite fascies metamorphism, even with this younger age. And through that, they've gone through pervasive intrusion, veining, and fluid alteration. And we see these really cool patterns, basically, where you've got a granitoid vein intruding. These are those kind of granitoids that were red on the map before. And next to the granitoid, we get a zone that's just full of phlogopite, or sometimes biotite. Then we get a zone of anthophilites, then we get these carbonates, and then we get a phlogopite peridotite, or an amphibole-bearing peridotite, depending on exactly where the rocks are. We're also not sure if any of the orthoperoxene in this is primary, because we see way more orthoperoxene next to these big veins. We also see it in talc carbonate veins. And so it's possible that the whole thing was completely hosed during metamorphism. So what I'm trying to say here is that when we look at the silicate mineral assemblages, these are purely just reflecting the metamorphism. But there is a possibility that the chromite compositions were preserved, and this is where that inference that it was a komatiitic, bonanitic, or basaltic magma came from. But when we look at the chromite in the peridotite and the silicate-dominated samples, it is pervasively altered. So on this ternary plot, the corners have moved again, so chromium's up here now. All of the peridotite-hosted chromites, the kind of disseminated chromites, have relatively high iron 3+, and this is not consistent with being formed from an ultramafic magma. And on top of that, in the more chromite-poor rocks, the spinel actually kind of splits into these 2 compositions. You start to get an aluminium-rich phase, and you start to get a very, very iron 3+ rich phase, almost or reaching magnetite in some cases. But some of these massive chromatites that I was doing the osmium isotope work on seem to retain primary compositions. And we think what's happening here is obviously these have been subjected to the same amount of metamorphism and fluid flow as the rest of the intrusion. But basically, when you have a rock that's got more than 80% chromite, you can bake it and you can cook it and you can add fluids and mess around with the silicates. But essentially, the chromite, the minerals that are hosted in the chromite, are just equilibrating with themselves. So basically, the chromite composition is buffered by the fact that it's just so much chromite. And some of these samples here are up to 92% chromite, and we think they're probably preserving primary compositions. But because we couldn't distinguish between these different sources using the major elements, we looked at using trace elements. And Akiya is kind of a stats whiz, so he did this thing called independent component analysis. This is basically a slightly more sophisticated version of principal component analysis, if any of you have worked with that. And so the idea with principal component and independent component analysis is that you, rather than looking at, say, like a pair of elements and plotting them up on a plot, you plot all of your data in a multi-dimensional space where each dimension is a different element. So you can think of this in a 3D plot. You would get some kind of cloud of data, right? And maybe it's like vaguely hot dog shaped. And the principal component, the first principal component, would be the one that explains the biggest variance in the data, so the longest axis of that big cloud of data. And obviously this is happening with many, many elements, so we have to deal with 20-dimensional spaces. But the whole point in doing this PCA, or ICA, the independent component version, is that we reduce the dimensionality so that we can plot stuff up, in this case just using one variable. So this is a plot of the IC1, the biggest independent component in a massive global database of spinel trace elements. And what we can see here is when we plot up this IC1, the Udrexuit massive chromatites overlap with most or many other layered intrusions, and statistically we cannot distinguish these from a komatiitic melt. They are identical. But we can distinguish them from the overwhelming majority of bonanites. And the reason for this, it's not what you might think, that it's picking up on the fluids, flux melting or something like that. It's basically picking up the fact that bonanitic sources are more depleted. But there is a certain type of bonanite, and this is from the trudosophiolite in Cyprus, that actually overlaps the komatiites better than it overlaps the other bonanites, and it overlaps the Udrexuit chromatite. So we've ruled out many other options, but we're basically down to it could be a komatiite or it could be a not particularly depleted bonanite. So this is just showing it in a kind of conventional trace element diagram. You can see here the yellow squares are Udrexuit. The red triangles with black borders are komatiites, and you can see there's a pretty good overlap. And then picrites and high magnesium basalts are over here. Most bonanites are down here, although we have shockingly little data. And these are the Trudos bonanites, the less depleted ones. So we can't rule them out with trace elements. But with looking at platinum group elements, we can actually see there's a massive difference between the komatiites that have relatively high iridium, ruthenium, and rhodium compared to the bonanites that particularly have quite low and variable iridium. And without going into masses of detail about this, this seems to be some destabilizing effect of fluids in a subduction zone that messes up the osmium and iridium concentrations, and that we obviously don't see in komatiites. So basically, putting all this together, we can say that the Udrexuit intrusion came from komatiitic parental melts, and that does imply a plume setting. Okay, so just to summarize that, for any PhD student in here, if your supervisor asks you to do platinum osmium dating, just say no. The rhenium osmium isotopes in chromite can provide meaningful estimates of igneous ages, and chromite can carry useful petrogenetic information even when all other minerals are completely altered. And finally, the trace and platinum group elements of chromite can really improve our ability to detect different parental melts or sources of chromite. Okay. So next I'm going to present some ongoing research, which is the subject of my ERC grant, and hopefully by going through all this, you know the answer already, and you're just going to spot this before I even explain it. But what we're trying to get at with this project is at continental crustal growth, and when I say that, I mean how and when the continents formed. So if we look at the early Earth, about 4 billion years ago, there was probably only one type of crust, so we probably had a uniform thickness of crust across the globe. And because of that, we have the same amount of water, and we have some evidence that was liquid water, so the Earth was probably covered in a global ocean a couple of kilometers thick. But if we look at the present day, we have this bimodal arrangement where we have thick continental crust and we have thin and low-lying oceanic crust. And because of that bimodality, we have exposed land and we have oceans. So we're trying to figure out how this process of splitting this initial single thickness crust into this bimodal modern crust that we know today happened. So the problem we have right now is that most approaches that have tried to do this are based on the mineral zircon. It's not exclusively zircon, but all existing approaches are really heavily biased towards felsic crustal growth. Now this is a problem because even if we look at the modern continents, they are andesitic composition on average, they are not granitic. And so we have a kind of 50-50 mix of more mafic basaltic compositions and more felsic granitic compositions. On top of that, the first stage of making any continental crust, you have to melt the mantle, and we start off making a mafic melt, and then it's only by reprocessing that initial mafic crust that we end up with something felsic. And finally, as we go further back in Earth history, the average crustal composition seems to get more and more mafic. And this is a bit debated, but I think there's some good evidence for it, so I'll just leave it at that. So what I was trying to do is develop chromite to kind of like fight for the missing mafic crust that's left out of our stories, and use mafic crustal growth, use detrital chromite to study mafic crustal growth in the way that detrital zircon is used to study felsic crustal growth. Okay, So, why chromite? I think, hopefully, this is starting to come together. So, chromite is ubiquitous in mafic and ultramafic rocks. It is robust, it is datable, and it carries information about its sources. And this is all stuff we've talked about so far. So what are we looking for? Well, our target rocks are this kind of rare rock type called a fuchsitic quartzite, and they're mainly restricted to the Archean. These are chromite-rich clastic metasediments. And I've got a picture down here. They have this really vibrant green color because the presence of chromite, when it gets metamorphosed, you make micas, and the chromium coming out of chromite is enough to give these micas a really, really vibrant green color. This is also really handy because a lot of people who make maps, or a lot of sedimentary geologists who study Archean sediments, are not good at identifying chromite, but they can usually write down when the rock is bright fucking green. So when I try and find these locations, it's a lot of poring over old survey reports and looking through reports of green rocks, and sometimes they're like green quartz veins with parallel laminations. It sounds a bit like it might be a fuchsitic quartzite. Having said that, we don't always see this green color. So this is from a drill core, and you can see there's just these black laminations, which are almost pure chromite in these layers, in basically a sandstone. And they are pretty rare in the recent past. They're relatively common in the Archean. They're not super common just because there's not that much clastic sediment around until you hit about 3 billion years or so. But this might be evidence for the average Archean crust being more mafic. Okay. So this project is kind of split into 3 parts, and the first part is to further develop this idea of using chromite trace elements to distinguish different settings. And this is work that's being done by Akuya and Emil at the minute, and they've expanded this global compilation. I think we've got about 4,000 different averages of chromite composition, so 4,000 different rock samples. And this is just a very, very broad split into mantle chromatites, disseminated mantle chromites, intrusions in yellow here, and lavas in green. And you can see that there is some separation between these groups. It's not perfect. But we would like to identify which trace elements are best for recording primary, igneous, or mantle processes, and then which of these can then best distinguish potential sources for these detrital chromites. The next part is studying crustal growth in the western superior craton. And obviously the superior craton is massive. We focused on the western part here because it has a lot of these chromite-bearing quartzites. So mostly fuchsitic, because it's mostly been up to green schistite and privilite facies. And what's really cool about this area is most of the greenstone belts have a basal quartzite sequence, and then they have mafic magmas erupted on top. So this gives us a better shot at getting sources that are not represented in the preserved rock record. And so Shreya and Emil are working on this, and then we've been working with Rasmus Haugaard at Laurentian University. And so far, we've got chromites from these 3 sites. We're hoping to go back this year, but we kind of hit all the easy targets last year, and now I'm really, really struggling with getting through some of the fly-in communities up here where our next targets are. But the idea with this project is to build a kind of, western superior mafic crustal growth curve and combine that with the zircon uranium lead and hafnium isotope record to try and get the felsic crustal growth curve, and hopefully we can get an entire kind of distribution through time of when this part of the superior craton was built. And finally, Kara up here in the top corner is working on searching for chromites that could have been eroded out of some of Earth's earliest mafic crust. So we're basically focusing on Archean sedimentary samples that are either really, really old or that we have independent evidence that there are ancient sources. And so we have some sandstones from Ishua that have been dated with zircon to be about 3.8 to 3.9. Kara found 1 chromite so far, which was very exciting, but she didn't find any more, so we'll see whether that goes anywhere. But the other target that she's currently working on a lot is from the green sandstone bed in the Barberton Greenstone Belt. And this is pretty notable because the Barberton Greenstone Belt and the Capval Craton, nothing is older than 3.5 billion years old within the Greenstone Belt. And actually, in terms of preserved rocks in the Capval, nothing is older than about 3.6. But it has 4 billion year old zircons in it. And Kara's preliminary work here seems to show that the chromite compositions, these are melts calculated to be in equilibrium with these chromites, do not overlap the known komatiites in the belt. So we have at least a possibility here, it's very preliminary, that these are being sourced from outside the Barberton Greenstone Belt, and they could be older than the preserved 3.5 to 3.2 billion year old sequence. So, hopefully you're all asking, this is a lot of kind of marketing speak. Does it actually work? I think the rhenium osmium dating part probably works. And this is from a proof of concept paper that Rasmus Haugaard and I did in the slave craton. And this plot on the side here shows the rhenium osmium ages of a few of these detrital chromite samples that we measured. These represent two localities which are fairly widely spaced. I think it's about 70 kilometers apart. We also have the uranium-lead zircon record. The purple curve is just the UPB ages, and the orange curve here is the hafnium model ages. So the idea here is the purple curve is when the zircon's crystallized. The orange curve is when that crust was initially extracted from the mantle. So not necessarily the same age. And then on top of that, we've got the whole rock neodymium isotope record for a different unit here in the slave craton. And what you can see is that our detrital chromite ages from these widely spaced localities give a consistent rhenium osmium age of about 3.2 billion years old. On top of that, it overlaps with the uranium lead peak, but it doesn't overlap with the hafnium isotope peak. So if someone was looking at this kind of naively and you just look at the zircon record, you would say that this is a major crustal reworking event, but there was no juvenile crust added. But actually it looks like there was juvenile mafic ultramafic crust added that potentially provided the heat to make these zircons grow. So I think this is a newly recognized crustal growth event, although, yeah, you might argue that you could sort of see it in the zircon record. But what about identifying the chromite sources? So trying to figure out what the actual source rocks of this. So we published this with this very bold title, Detrital Chromites Reveal Slave Cratons Missing Comartite, because the slave craton is one of the only cratons that doesn't have any comartites preserved. But despite making this kind of bold claim, we're not really sure that these chromites were comartite source. And this was criticized by Stannon et al. 2021. And if any of the students or postdocs want to see a masterclass in shooting down someone's idea very, very politely, then I would recommend reading this paper, because they basically presented what we'd said and then said, actually, with our data, this can't work. But we're only talking about our data. Very, very polite, but I think they were right. So basically, they argued that the chromium numbers of our chromite were probably too low to actually be comartiated. And a couple of things come out of this is that basically we do need to expand the range of elements that we're using, as I mentioned with the trace elements before, and we probably need better controls on metamorphism, because Stannon et al. Did a much better job of that than we did. Okay, and I'll just summarize that. So mafic crust is really underrepresented in our continental crustal growth story, but because of all the stuff I've been talking about during this talk, chromite is robust, it's datable, and it carries all this petrogenetic information. I hope that we can develop it as a tool to track mafic crustal growth using these chromite-bearing sediments. And so far, the dating side of things seems to work. Identifying crustal sources is a work in progress, but we are working on it and we're trying to get better. So, yeah, that's all I have. Thank you very much.